All right, next up, we have our lightning talks. And our first presenters are going to be Ian Flint and Igor Gashinsky from Yahoo, telling us all about UDPing. Take it away, guys.
Hey everyone. So how many people have something like this in their network? Bunch of lags, fully meshed between your routers, and somebody says, I have a performance issue from source to destination. What the hell do you do? And that's actually the simple case. But make that go all the way across the country, where you have multiple hops of this. How do you detect, monitor, troubleshoot? The usual method is, well, not pretty. You basically start taking links out of service or city pairs out of service until you find whatever's causing the problem. And if it's 0.5% packet loss or something along those lines, it might take you a couple of days. Well, as you can imagine, in a large-scale production network, that doesn't work so well. Also, we have heard for many years that there's going to be solutions to this. There's going to be BFD that works for lag that will detect this. There's going to be Ethernet O&M. There's going to be some other magic thingy. And I think after waiting for close to a decade, we decided that we need to do something about it. So here's Ian to talk about what you do.
Hello. So what we built to solve this problem is something we're calling UDPing. What UDPing does, it's an evolution of the one-way active management protocol. So it sends a stream of UDP packets from a client to a server. The packets are emitted in groups. We chop them into groups of packets, and each of the packets, we timestamp it at the client, and then we pick it up at the server and check the timestamp at the server to determine latency. And we put a serial number on every packet, which is a monotonically increasing serial number, so that we can detect packet loss by basically taking the difference between the last packet in a group and the first packet in a group and subtracting the number of packets we received. So if the first and last packets are 20 packets apart and we received 19, we know we lost a packet. On the server side, we've got a server that receives the packets, timestamps them as they come in, does the loss detection, and then emits statistics to either statsd or standard out. So the features, that's all very nice, but what was really a challenge was to make this useful in a complex networking environment like what Igor described. So we do a lot of tricks to make this thing sort of ferret out as many problems as we possibly can. So the first is we do true one-way measurement. This means we can measure the quality of service in one direction versus another. So if we have a funny route in one way that isn't the other way, we can actually isolate that problem. We spread the traffic across multiple next hop gateways. The way we do that is we actually write the Ethernet frame and we manipulate next hop MAC so that we can force the traffic to go to either the primary or the secondary router out of the network that we're emitting from. We manipulate the source port so we can exercise, if we have multiple ECMP pathways, we can exercise all of those, and you can do, since we're writing the link level header, we can use as many source ports as we want to. You don't actually have to bind to a UDP socket or to a UDP port. You just throw the packets on the wire and they go. So that makes it very nice, and it makes it easy to deconflict multiple instances of UDPing running on a single client machine. Randomize the payload size, so you can detect like MSS failures. You can say, I want to push right up to my MSS and see if it makes it across or if it gets fragmented and lost, or if there's any particular issues with a particular packet size. I know we've had a few of those problems in our network. The other thing that we were really concerned about was resonance. And so if you emit a packet once a second, or if you emit a packet once every half second or once every tenth of a second, maybe there's an event that happens every second or every half second or every tenth of a second that just happens to miss every packet that you send, or just happens to hit every packet that you send. So there's a randomization method called Poisson sampling. It's based on an exponential curve, and what it does is it allows you to do random intervals between packets and yet still have your emission frequency average to a fixed number that you want to go after. And finally, we collect statistics that allow you to take the output of statsd and turn it into jitter measurement. By doing sum of squares, you can do a rough approximation of standard deviation across a set of packets. We also emit a sum and count and maximum latency. What's nice about these statistics as well is that they're additive. So you can do standard deviation across a single group, or you can do standard deviation across 10 groups, or across 10 minutes, or across an hour, whatever you want to do. It all adds up and the math works out. So as far as deploying this in Yahoo, what we did was we started out by rolling it strictly for point-to-point links.
Yeah, so you guys remember how I talked about what happens when you have, how do you identify where the problem is? Well, one way you do it across a global backbone is you simply say, I'm going to test every city pair. And if I have a problem from one end to another, well, the city pair that is having the problem, that UDPing will hopefully identify that city pair. At that point, you still will have to do the standard binary division, take out enough links, and see where the problem is. But at least it zooms in on where the problem is, which is usually the hardest part of the whole thing.
Yeah, and I mean, the other thing is, when we moved to UDPing from a simple ICMP probe. The problem with an ICMP probe is it only exercises one path, where you may have 16, 32, however many paths between between a city pair. And so it does guarantee that you're spreading your traffic out across your entire network footprint, rather than only exercising a small portion of it. So we started out by doing this in a point-to-point deployment. We basically put it in every POP on our backbone, and we measured single hop latency, single hop packet loss across all those, and emitted alerts to our monitoring console. The next step was to deploy a full mesh across our backbone. And so every single POP, every single site, we put one of these agents in, and we set it up to do a full mesh to every other POP and site. And we're able to draw a nice grid, which on a good day is all green, and look at the performance of our backbone as a whole. The next thing we're planning to do is our data centers at Yahoo are split into availability zones. And so we want to deploy this into every availability zone and build a full mesh between availability zones, which will give us a couple of things. It'll give us more redundancy in terms of our coverage of our backbone. If you only deploy to a single box in each POP in your backbone, that box becomes a single point of failure. But if you deploy to multiple AZs within a site, you have that redundancy, and you can actually tell the difference between a single box failure and a backbone failure.
And one of the reasons that we do that is, if you think about it, let's say you have packet loss from DC to Bay Area. So phase 2 is what we'll say, hey, you have a problem from DC to Bay Area. On top of it, you have every point-to-point link that says, hey, I have a little problem between actually Chicago and Denver. So now that kind of zooms you in on where you need to begin troubleshooting. By having multiple overlapping layers of monitoring, you effectively can say, I have a problem from here to here, and this is actually the problem. And even with a simple example of New York to Chicago, well, on that example, you had 4 different paths, effectively all lag. You could see, is the packet loss 25% there? Okay, it's one of the lag members. Is the packet loss 50%? Probably one of the routers. Is it 1%? Okay, one of the links is being flaky. It really allows you, by having multiple overlapping layers, to troubleshoot and zoom in, which you have to work on. And best part of it all, it allows you to figure that out, at least with UDPing, 10,000 packets per second?
Over the whole backbone,
yeah
about that. We're running
so
about that.
With about 10,000 PPS, you can detect it hopefully way before your applications do.
Yeah, it's extremely lightweight. It's fully written in C. I think the memory size of it's like less than 50K. So you can run it, and it barely has a footprint on the hosts that you're running it on. So the best news, I don't know if you've caught the lower right-hand corner of the last few slides, but it's open sourced. And so you're free to download it, fork it, use it as you see fit. Contribute back. We'd love to get any improvements that you might have to it. github.com/yahoo/UDPing. That closes the talk. Any questions?
Guess you have 27 seconds left.
Actually, we're going to hold questions until the end of the lightning talks if we have time for that. If not, you're more than welcome to come up and, talk to Ian and Igor afterwards. But thank you very much, guys.